All right. So we have a question about section 5.4, number 8. So let's take a look at this. So I'm going to share my browser window so we can look at this together. 5.4, number 8. Let's see. Here we are. Okay, so we've got we want to find the volume of a right pyramid. Right pyramid means that the vertex is exactly above the center of the base. So if you cut it in half down the middle, it's a right triangle from the side. It has a square base in the xy plane. X is between -1 and 1, y is between -1 and 1. And the vertex is in my problem, vertex is at 0, 0, 1. And this varies from problem to problem. And unfortunately, the picture doesn't quite reflect where the vertex is. But they tell you the graph shows a pyramid with the vertex at 0, 0, 3. So you have to your problem may have different values for the vertex. You're going to have to think about how yours might look a little bit different. All it's going to do is just lower or raise the position of this vertex. In my problem, the vertex is at 0, 0, 1. So I'm going to imagine that this is height 1 here. Okay, so compute the volume of 1/4 of the pyramid. Oh, this is the hint. Compute the volume of 1/4 of the pyramid and then multiply the answer by 4. Well, that makes sense. So what we're going to do here, I gave a hint for this in the forums, and I suggested that you think about the region at the base of the pyramid and think about, I forgot what I suggested. Let's see. Oh yes, yes. Okay, I remember. Okay, so let's go to the paper here. If I can turn off this shared view of my screen. There it is. Lost the button. Okay, so we'll go down to the paper. You should be seeing the sheet of paper. So the base of the pyramid is a square, right? So and x went from -1 to 1, and y went from -1 to 1. Right, so that makes this square base. Okay. Now the hint was that we should just look at 1/4 of the pyramid and find the volume of that, and then we'll just multiply it by 4. So the 1/4 of the pyramid that we want to look at is actually this one. This is what I specified in my hint. So just this, the part of the pyramid that's above this triangle. So what we want to do to find the volume, you can think about this 2 different ways. You can think of the pyramid as being a function that lives above this, right? And then you're just integrating that function over this region, and that will give you the volume, okay? Or you can think, that would be thinking of it as a double integral. So approach 1, as a double integral, you could just say that I'm going to integrate over this. Let's call this region R for region. I'm going to integrate over R of the function of xy, and that function of xy is the height of my pyramid, right? So that's what gives it its 3-dimensionality there. And I'll just do this double integral. Of course, we are in the section involving triple integrals. So let's do it that way instead. Approach 2, and you'll see they're really the same, as a triple integral. And we'll be doing let's use P for pyramid, and triple integral over the entire pyramid of the function 1 dv. This is a different approach as a triple integral. And when you want to find the volume, you just integrate the function 1. So in the first approach, you're finding the volume underneath the graph over an area, right? And the second part, in the second approach, you're finding just the volume of a region. So you just integrate the function 1, all right? They'll give you the same answer. And they really are, when you work them out, you'll see they actually just do the exact same thing. Let's do it using this triple integral. We want to position ourselves in this region and then integrate upwards to the top of the pyramid. All right, now the top varies depending on where we are. So what you could do is first think about specifying an x in here. So for each x between 0 and 1, what's y going to range from? Well, for each x, y is going to range from here up to here. So I get a line segment. So for each x, y ranges from this height, which is on this line, and this line, I can just see it's a diagonal line, 45 degrees below the x-axis. That's just the line y equals negative x. And then I go up to this line. This line is y equals x. So for each x, y is going to range from negative x to positive x. That went off the screen there, sorry. Negative x to positive x. And then for each x and y that we find ourselves at on this line segment, we're going to integrate z from the base of the pyramid to the top. So z is going to start at 0 and go up to the top of the pyramid. All right, now the top of the pyramid is a function of x and y. Okay, so let's write down this triple integral and then we'll figure out what that function of x and y is. Well, maybe I'll leave that for you to figure out. So we have our triple integral of 1. And now I started this by doing x first. So x goes on the outside, all right? The integral kind of does things in reverse. So when I was thinking about it, I thought about first positioning an x between 0 and 1. And then for each of those x's, I found a y. Y ranged from negative x to positive x. And then for each x and y, I thought about what z ranged from. Z is going to go from 0 to the height of the pyramid. So above any point x, y here, I go up to the height of the pyramid. And you can express that as a function of x and y. All right, so that's going to be a function of x and y here. And that's going to be the height of the pyramid. Okay. And you'll see that when you do this first integral with respect to z, this triple integral will become the double integral that I mentioned up here. So these are actually doing the exact same thing, right? Because as soon as you get through the dz integral, you're on to this. So both approaches are actually the same. How do you get the height of the pyramid? Well, if we look back at the pyramid, let me go back there. So we should be seeing my browser again. And if we look at the pyramid, we can see that above the region that I specified, above that triangular region, the pyramid is just this, let's see, is it this surface or is it this one? I think it's, it's this surface right here. Yeah. So this surface on the right-hand side of the pyramid is just a flat surface. So it is given, it is a plane, right? So you know how to find the equation of a plane well, if you know 3 points on a plane, you know how to get the equation. We talked about this back in chapter, I don't know, I'm going to guess chapter 3. We talked about finding the equation of a plane given 3 points, and I can clearly see 3 points on this plane, right here, here, and at the top. The top is actually given to you. They gave that as the vertex, right? So use those 3 points to find the equation for this plane, and then you can find the function of xy that specifies the height of the plane above every point xy. And that will be that function that I specified, f of xy, in that integral. Now, the question, one of the questions that was asked here was, let me go back to the sheet. Okay. When you do this integral with respect to a, can you just use the area of this region using the formula 1/2 base times height for the area of a triangle? And the answer there is no. You can't do that, and that is because if everything was constant if the height was constant throughout this triangle, then you could do something like that. But the height is not constant throughout this triangle. The height of the pyramid varies as I move from one point on this triangle to another point. And so I can't treat the triangle as just one uniform thing and just do 1/2 base times height to get the area and multiply the area times the height, because the height isn't constant throughout the triangle. So no, you can't just use the area of the triangle formula 1/2 base times height in this problem. We really have to break it down to point by point, as we did in how we constructed this integral to do this problem. Now remember, once you get this answer here, that's only 1/4 of the volume. So at the final step of this answer, the volume will be 4 times this. Right? So don't forget that last step. Okay? So that's how we're going to do that. I hope that helped. Are there any other questions with the last homeworks? Not seeing anything coming in here. So the question is f of xy in this case equal to 1? Well, not the f of xy that I specified, right? So the f of xy that I specified here represents the height of the pyramid. And so the height of the pyramid definitely varies, right? It's not just a flat horizontal sheet. It's a tilted sheet. So it depends on your position xy. So the fxy that I wrote down here is not equal to 1. This represents the height of the pyramid. I think I know what you're thinking. You're thinking that I'm finding the volume, so I should be integrating the number 1. And we did do that. We integrated the number 1, but what we did is we let z range from 0 to the height of the pyramid. And so the f of xy represents the upper z bound. So you're going to get an expression in xy for the height of z. So f of xy will not be 1 in this case. That's not the f of xy is not the thing that goes in the, it's not the integrand in the triple integral. It is the height that z goes to. It does happen to be the integrand in the double integral, if you set it up that way, but it's not the integrand in the triple integral. There was another problem. You might have had questions about this one, so I'm going to go and pretend like you asked this. Somebody did ask this in the forums. So let me go and try to find this problem. Let's share my browser again. I'm not sure if it must have been in this homework set here, but maybe it wasn't. Let's go through it here. This one. Maybe I should have put this problem here, number 5. closer to the end of the homework set, because I think it, maybe not, I don't know. It might be a little bit more challenging than the other ones, I'm not sure. So I had some questions about this one, and I looked at it and I said, yeah, that one requires a little bit of thought. So maybe it's worthwhile to go through this one a little bit with you as well. Find this integral, the integrand here is just y, where E, the region we're integrating over, is the solid bounded by these curves. All right, so just give me a second. I'm going to write these on my sheet, and then I'll switch the view back to the sheet. Okay, and like I said, this was the question about this was given in the forum. Okay, so what we're doing is we're finding a triple integral over a region of y dv, where R is given by the region bounded by these curves. So R is bounded by these things. All right. So if I start graphing these, and it takes, you know, the first time I started sketching the graph, I messed it up. So don't feel bad if that happens to you. It's not complete. It won't be as simple as I'm making it look now, because I've already done this. But you know, I did it once. I'm like, oh no, that's probably not the right way to sketch it. I'll try again. So if you don't get it right the first time, don't feel bad. Let's see. In the first equation here, z equals x squared. That's just a parabola, right? So, oops. So here's the z-axis, here's the x-axis, right? So z equals x squared is a parabola. And I'm going to put dashed lines back here because I feel like in the volume this is going to be behind. All right, I know that ahead of time because I've already done this. So here's this parabola, all right? Z equals x squared. Y equals 0. Well, that's just, that is just the plane. That's just the xz plane. So the back of this surface is just going to be the xz plane. So I'm not going to go anywhere behind this, right? So all that stuff is out of there. And then z equals 12 minus 4y. Well, 12 minus 4y is just a linear function. That's in the form mx plus b, right? So that's just a line. It has z-intercept 12. So up here on the z-axis, I'm going to have height 12. And it's going to be a line that slopes downwards like this, and then comes and intersects the y-axis. Well, what does y have to be to make z 0? Well, y has to be 3. All right, so that's a line that intersects the z-axis at 12 and the y-axis at 3. And what am I bounding here? What region? Well, the back is the xz plane, so I'm not going anything behind that. I'm below this line. This is actually a plane. If we go off of the yz plane here and then include the x variable, you extend this in the x direction, you actually get a plane. So we're below this plane, but above this parabolic cylinder. So what I'm seeing here is I'm below this plane, above that cylinder. You actually get, if you think about it, you get a shape that looks like this. This is the three-dimensional region. We're below this plane up here, but above this parabolic cylinder. That's this part down here. And with this problem, there's several ways to set up this integral. I think so here's one way to set it up. All right, you can say that, well, I think the easiest way to do this is to find the values of x that are on the x-axis below these two corner points here. And that's not immediately obvious, but after I started setting it up one way, I realized, oh, it would be easier if I did this. So do it this way. Find what these points are here. Well, that's not too bad, because you see this is a parabola z equals x squared, right? So I know the height here is 12, so 12 equals x squared. So I know what my x is. X is the square root of 12. And negative root 12 back here. So I'm going from negative root 12 to root 12. So for each x between negative root 12 and root 12, I am going, so if I take an x in here, what's my z doing? Z is ranging from this height up to here. Okay, now I got to rewrite the number 12 because I just scribbled it out. Okay, so z is going from here to here. So what's the lowest point? Well, that's a point on the parabola. So z is starting at x squared, right? That's what z was given by here, and going up to this line. Well, this line is just 12. So for each x between negative root 12 and root 12, x goes from z goes from x squared up to 12. Now I've specified for every x, I've specified a z. So now I got an xz. So now I have to find out is how far do I go out in the y direction until I hit this surface. Right? So just going out in the y direction here, eventually I'm going to hit the surface. You know, how far do I go out? Well, that's given by this. So the way I've just kind of thought this out was x I specified first, so that goes on the outside. Then z. The z was the next thing I did. And then y I did last, so it goes on the inside. X, I said, went from negative root 12 to root 12. Z went from x squared, oh, sorry. Yeah, x squared to 12. And then y goes from, I'm going to let you fill this stuff in on your own, all right? And it's going to come from this, right? So you can see y starts back here and goes up to the surface. So you can figure out what goes here and here. And that will be how you set up that integral. But that's not the only way to do it. In fact, the first time I started this problem, I did it a different way before I realized, oh, wait, this way is a little bit easier. But let me show you, there's another way to do it, and it's not that bad. Naively, I first thought, oh, the most obvious range here is the 0 to 12 in the back. So I'm going to let z range from 0 to 12. Right, so I'll get a z in here between 0 and 12. And so that'll be my outer integral. So outermost integral I'm doing with respect to z. And then for each z, I have to go to this curve and to that curve. And that's when I realized, oh, it might be easier the other way. But for each z, I'm going to this curve and this curve. Well, this curve comes from this. And I got to solve this for x, because I got to figure out how far out to go in the x direction. Well, x goes from up here. It's if you just solve this equation for x, you get x equals square root of z. And in the back, it goes to minus root z. Right. So that was what my x ranged from. And then y, same thing, right? Y behaves the same way it did in the integral above. I just didn't like this because I don't like having roots to have to integrate. I just feel like that's yucky, right? So when I saw these roots appear, I said, well, stop doing it this way. I'm going to try to do it without square roots. And I'd rather be integrating squares than square roots. So after doing approach 2 first, I said, oh, maybe approach 1 would be better. But there's actually other ways to set this up. In fact, somebody in the forums posted an alternative way to do it, where they actually found x and y. I think they did x and y, and then the z was the last thing they did, which makes sense too, because you've already got this solved for z. Right, so there's lots of ways to set this problem up. This is just 2 of them. In fact, I think there's 6 different permutations that will work here. You can permute these x, y, and z, 6 different orders, and I think all of those. Don't quote me on this, but I believe all of those will be doable in this triple integral setup. So it's not just one or 2 approaches here. There's lots of different ways to do this. Okay. So any other questions? I'm not seeing any. Okay. So what I'm going to do is I'm going to just talk about the next section, which is not it's not very much material. So I think it should go quick. I think we have plenty of time here. And the next section is, let me just check the section number. It's section 5.6, calculating centers of mass and moments of inertia. We're going to skip the moments of inertia business. I want to keep things simple. And once you know centers of mass, moments of inertia, it's easy to learn that on your own. It's not that big a difference. So this is section 5.6. Let me go to the sheet here. You should be seeing the sheet. Let me know if you're not. Calculating centers of mass. What is the center of mass? Well, the center of mass is the point within an object where it's the centermost point as far as the mass is concerned. I don't know another way to say it, but it has very, very important applications. So we're going to be doing this for two-dimensional shapes and also three-dimensional volumes. If you're dealing with a two-dimensional shape like a plate, you may want to know where to balance that plate on your finger. You want to know where would I put my finger so I could balance that plate. If the plate doesn't have uniform density, it may not be obvious where to balance it, right? And the center of mass is exactly that point. It's that point where you would want to balance it. And that's very important in physics because we want to know, when we think about objects, what is if we had to pick one point to, choose to represent that object, where should that point be located? And that's incredibly important when you do physics. And so finding that point is important there. It's also, if you think about in 3 dimensions, if you think about meteors, if you've ever seen pictures of meteors in outer space, they're spinning around in 3 dimensions, and they're usually spinning around more than one axis. They're always spinning around a single point though. And that point that they're spinning around is the center of mass. So it's important in that regard too, if you're dealing with 3-dimensional objects. And when we do physics, we can then, treat that meteor as if it's a single point in space if we use its center of mass. Okay, so that's why these things are important. Let me start with a very basic example where we do everything in one dimension. Okay, so in 1 dimension, imagine, I think a good example of this would just be a teeter-totter on a playground or a seesaw. So a teeter-totter or a seesaw in a playground, we're going to have this, it's just a plank balanced on a what they call a fulcrum. The fulcrum is the balancing point, which for a teeter-totter is going to be right in the middle. But imagine that 2 children come and sit on this teeter-totter. Now, if they have equal mass, how do they balance the teeter-totter? Well, of course, they should sit equidistant from that balancing point. So if their masses are the same, M1 and M2 are the same, they would balance themselves just by sitting equidistant from here. This balancing point is what we're going to call X bar. Okay? And that is what we also call the center of mass. Now, if one child is bigger than the other one, weighs more, then this picture is going to look a little bit different. Well, let's suppose the lighter child sits down first. So let's say M2 looks like this, and he sits down at the very end of the teeter-totter. Now, if the larger, older child comes by and sits in the same position on the other side, what's going to happen? Well, of course, the teeter-totter is going to tilt down in his direction, right? Because he weighs more. Just makes sense. But he can move on the teeter-totter to correct this, right? If he weighs more, what do? You move towards the fulcrum, right? So the larger child here, M1, will sit closer to the fulcrum to balance this. So again, the center of mass is now, it's the balancing point, but notice it's not equidistant to these two masses. What we find out here is we can treat the influence that these masses have on the situation just like torque, when we talked about torque way at the beginning of the class. If you remember, if you are tightening a bolt and you use a wrench to do it, right? You know that the further out you push down on this wrench, the more torque you generate, the easier it is to twist this bolt, right? And we learned that to compute the torque, you take the cross product of the force with this radial vector here, r. And torque was equal to, oh boy, I forgot if it was F cross R or R cross F. Well, I'll put a little question mark here because I don't remember exactly. I think it was actually R cross F, but I might be wrong. You should go check that in the book just to be sure. But it's essentially, you take the cross product here. And that gives you a vector coming out in 3 dimensions, coming out in the other direction. That determine the magnitude of that vector is the amount of, essentially the amount of twisting force that you're applying to this bolt. And the gist here is just the overall thing that's going on. You're essentially, I mean, this is really a cross product of vectors, but you're kind of essentially just kind of multiplying the force times the distance that you are out. Now there's more to it than that because the angle that you apply the force to comes into play here. But if we kind of just kind of take a, if we were measuring the wrench, I should have drawn the picture like this with the wrench horizontal, then that angle doesn't play a role because really, if you remember, the magnitude of the torque is the magnitude of it's the length of R times the length of F times the sine of the angle here, where the angle was, yeah, I believe it was this angle here. But if in the case where the wrench, if you're pulling directly down on a horizontal wrench, the sine of that angle is just 1, so it doesn't even play a role. And so you really are just multiplying the length R times the magnitude of the force F, and that gives you the torque. And you know, the further out the longer the wrench you have, the more torque you're going to apply. Well, what's force? Force is mass times acceleration. And in this teeter-totter business, the acceleration due to gravity is constant. It's the same for both masses. So that doesn't really play into here. So really, the influence that each mass has is just, the force is just, essentially boils down to just the mass. And the torque that person exerts is just the mass times the distance they are from the fulcrum. Okay, so you're going to find the influence of this mass, you're going to multiply it by the distance they are from the center here. So what we need to have happen for this to be balanced is that we need mass 1 multiplied by the distance here. Suppose this guy is at position x1. We need this mass 1 times this distance, that's absolute value x1 minus x bar, to be the same as basically the torque of this kid. So that's going to be m2 times his distance, the distance between x2 and x bar. If that equation holds, if these two sides are equal, then the teeter-totter will be balanced because they are exerting the same torque on the system. All right, well, I'm going to just unfold this equation a little bit so we can we want to get a formula for x bar. Right? We want to solve this for x bar. Okay, So x1 minus x bar in absolute values is really just x bar x minus x1, because x bar is bigger than x1. So I'm going to write this like this. And x2 minus x bar absolute values is just x2 minus x bar, because x2 is bigger than x bar. Oh, thanks, you corrected me, it's r cross f. Well, you didn't correct me, but you affirmed what I wrote. Good. That the torque really is r cross f. Thank you for looking that up. Okay, so we got, we multiplied through here. We got m1 x bar minus m1 x1 equals m2 x2 minus m2 x bar. I'm solving for x bar, so let's move the x bar terms to the left. Let's move the non-x bar terms to the right. Let's factor out the m1, let's factor out the x bar. All right, so this is really just m1 plus m2 times x bar. And I'm going to write this in order. So I'm going to write m1 x1 plus m2 x2 over here. And now I'm solving for x bar, so I'll divide through by m1 plus m2. Okay, so there's our formula for the center of mass. In the bottom, we have the sum of the masses. That's the total mass. And that's in the denominator. In the numerator, we have what they call the moment. That's the word they use for this. I'm not sure why that's the term they use, but that's the term they use, moment. And you get that by multiplying each mass times the distance from, well, just the position, just whatever coordinate it has. Now, it doesn't matter how you've positioned the coordinate system here. I could have the 0 sitting over here. I could have, my x-axis could be that, or I could have the x-axis with 0 over here. Or it doesn't matter what numbers I assign. It's kind of all relative. And so that doesn't even play a role. As long as you fix coordinates up there, however you decide to fix them, you could just run this formula, and this will be the center of mass with respect to that coordinate system. Right? So it doesn't even matter how we set things up to begin with. And this will give you the center of mass. Right? This is a one-dimensional situation. And this is also a situation where we just have two masses. But you know what? If you work it out for more than two masses, suppose we had a whole bunch of children jump onto this teeter-totter, same formula works, right? So in fact, x bar, you could actually do this for any number of children. You'd have each child, you'd take their mass and multiply by their position, and then you'd add them all up. Right? And then you'd divide by the sum of all the masses. That's the moment. And that's the total mass, just the sum of the masses. Okay? And we can even generalize this even further. We can imagine not just a finite number of children on here, but you could imagine a bar, trying to balance a bar whose density varies as we move across the bar. So maybe it's really thick and dense on one end, and then it's very thin and light on the other end. Right? And so how would you balance that bar? Well, you can imagine this kind of like the same problem where at each point on the bar, you've got a different amount of mass, right? Because it's different densities as we move throughout the bar. And so now it's like having an infinite number of children sitting on this object, each one with slightly different mass. And so we can think about that situation. So we can think about the balancing point of a bar of varying density. Okay. And so we might say that the density is well, we would say that the density is a function of your position on the bar. So I would call that rho of x. Rho is usually what we use for density in physics. So the rho, this is the Greek letter rho, and it looks like a P with a curly tail. Right? So the density depends on x. Okay. So this is the linear density. So it's the density per unit length. So it's the amount of kilograms per centimeter or amount of pounds per inch. All right, so if you want to get back to the mass, what we would do is we'd multiply the density times the small amount of distance. So if you take pounds per inch and multiply by inches, you get back to pounds. All right, or kilograms per centimeter, you'd multiply by centimeters, you get back to kilograms. So we can get back to mass from density just by multiplying by length. All right, so the picture looks like this. We've got this bar. Now, I'm not putting this in the center because maybe the bar weighs a little bit more over here than it does over here. It's more dense here than there. Right? So we imagine an x-axis down here. Doesn't matter where we position it, where 0 is, does not matter. What we're going to do is for each x, we're going to look at how much, essentially, the infinitesimal mass at this point over here. So the infinitesimal mass, because we're doing this over an infinitesimally small length of the wire, is going to be, it's going to be the density times an infinitesimal length. Well, that infinitesimal length, we call that, in calculus, we call that dx. So you imagine a little tiny little length that what we're going to do later is going to take the limit as that length goes to 0. And that's what makes it infinitesimal. Right? So it's going to be the mass multiplied by dx. Sorry, the density, I may have said the mass is going to be the density multiplied by the infinitesimal length. So kilograms per centimeter multiplied by centimeters gives you kilograms. So that gives you the infinitesimal mass. And so what we're doing is we're adding up all these infinitesimal masses. That's what this formula is saying to do. Add up all those infinitesimal masses, and that should give you the numerator here. Well, when you add up an infinitely many infinitesimal parts, that's called an integral. That's what an integral is. It's just adding up infinitely many infinitesimally small things. So what does this become? All right. The center of mass, therefore, is the integral of, look what we did up here. We multiplied the mass times x. Well, how are we getting the mass? It's rho of x dx. So we're going to multiply this by x. All right? So if this is what's going in place of m. All right? So, and then we're going to multiply that by x. So really, we're integrating x times rho of x dx. Rho of x dx is the mass, and then x is the position from the center. And then we're going to divide by the total mass. How do you get the total mass? Well, you just add up all the infinitesimal masses. But we're adding up infinitely many of them, and they're infinitely small, so this is the integral of the infinitesimal masses. So this down here is the total mass, and this up here is the moment. And this is how you do this for a continuous problem, where the density continuously varies across the wire. Okay. All right. So, give me a second. I had a little, I had some notes here, but I seem to have misplaced them. There we are. Okay, so right. So now what I want to do is I want to look at balancing a plate, all right, a two-dimensional plate. Or maybe, you know what we should do? Let's do an example of this one before we do that. So let's do an example. It's always good to do examples to make sure we fully understand what we're talking about. So, example. What I'm going to do is say that the density of a wire is given by x minus 1 squared. And the wire extends from -2 to 2. Okay, so what we're doing is we're looking at on the x-axis from -2 to 2, we've got this wire. It's extending from here to here, and it has varying density. This is actually called the linear density. Really, density is like kilograms per cubic centimeter, but here we're thinking about kilograms per centimeter. So this is the linear density. So we want to find, what we want to do is we want to find the center of mass. Where would we balance this wire? Center of mass. Okay. You have to excuse me. I'm running out of paper, so I'm reusing old paper, which got some writing on it already. So you can just ignore that. Find the center of mass. Let's see. So here's the formula up here, right? So we've got our density. What we're going to do is we're going to multiply that by x to get our moment, right? So we're going to find the moment. Is going to be the integral from -2 to 2, because that's where this wire lives, of x times x minus 1 squared, x times rho of x dx. That's it, right? That will be, let's see, this will be the integral from -2 to 2. Let's see, this is x squared minus 2x plus 1. So this, when I multiply by x, I get x cubed minus 2x squared plus x when I multiply that out. All right. So then we anti-differentiate. We get 1/4 x to the 4th minus 2/3 x cubed plus 1/2 x squared, evaluated from -2 to 2. Let me just quickly run that in a, well, oops, pushed the wrong button here. That's going to be annoying because that program takes a long time to load. Okay, let's try to work it out by hand then. Okay, so this is 2 to the 4th is 16, divided by 4 is 4. All right, so that's 4. This is 8 times, so 2 cubed is 8 times 2 is 16, divided by 3. And then 2 squared divided by 2 is just 2. That's what I get when I plug in positive 2. When I plug in -2, I get, again, 4. This is going to be, is a negative and a negative make a positive. And then this, again, gives me 2 here. So the 4's cancel, the 2's cancel. So I really just have -16/3 minus 16/3. So that's minus 32/3. That wasn't too bad. All right, that's the moment. We also need to get the total mass here. Well, that's just the integral from -2 to 2 of x minus 1 squared dx. Okay. Let me work that one out really quickly here. I'm just going to use Maple to do that one. Not that it's hard. I mean, it's easier than the last one we did. I just want to be quick about it. X minus 1 squared. If you work that out, you should get to 28/3. Okay. And so the center of mass is going to be the moment divided by the total. The moment of mass divided by the total mass, right? Well, the 3's cancel here. I can multiply the numerator denominator by 3. So this is just negative 32 over 28, which is negative 16 over 14. Just divide by 2 again, negative 8 over 7. Negative 8/7. Right? Now, where does that look like? What does that look like in the picture? Well, it's somewhere, it's a little bit less than negative 1. So it looks like the fulcrum would actually be positioned right there. So it's very heavily weighted towards the left-hand side. Looks like there's a lot of mass in this region and not very much mass over here. And if you look at a graph of the density, you'll see that makes a lot of sense. Okay. So that's a linear density problem. We can also do densities. We could also find center of mass for like a plate, a two-dimensional region. Okay. So, for instance, everything all right? Yeah. So, for instance, and this is number 297 in your book. What they have here is they have a plate shaped like a triangle. Like this. And this is your region. And they say that the density is now a function of two variables, excuse me, and it's given by x times y. Now, how do we find the center of mass here? So what we have here is we have a triangular shaped flat surface. And I want to know, where do I put my finger underneath this thing to balance it on my finger so that it stays perfectly balanced? Where's that center of mass? Okay, well, the trick to this problem is we have to break it down into two. We need to find the center of mass in the x direction, and then we have to find the center of mass in the y direction. Okay, so what we do is we take any point in here, right, some point xy. We know the density at that point. So we can find the infinitesimal mass at that point. So the infinitesimal mass at xy, well, here, the density here for a plate in a two-dimensional problem, now it's not the linear density, it's the square density. Right? The square density is mass per square, per unit, per area. Right? It's the mass per area, not the mass per length. So it's going to be like kilograms per square centimeter or pounds per square inch. That's what the square density is, all right? Two-dimensional density. So if I want to get back to mass, I'll multiply the density times area, right? So the infinitesimal mass is going to be the mass at the point multiplied by dA. Instead of dx, the next step up, the two-dimensional version is dA. So we're imagining multiplying the density times a little chunk of area. Right? And so the total mass is going to be given by integrating all these. You just add up all the infinitesimal masses. Well, that's going to be the double integral over that region of rho of xy dA. That's how you get the total mass. Just same formula as before. We're just doing a double integral with respect to dA instead of a single integral with respect to dx. Now, here's the part that's a little bit different. I need to find the center of mass in the x direction. This is the x bar. Where do I put my finger in the x direction to balance this? Well, it's the same idea. We're just going to weight everything by its position x. And so what I'm going to do is I'm going to take the double integral over the region and multiply the integrand by x. It's still a double integral. I'm integrating with respect to x and y, but I'm weighting with respect to x. Weighting with a t. It's my weight. It's how much emphasis I'm putting on that particular point. All right? And then I can compute my y bar. My y bar is going to be the double integral, and you guessed it. I know you know what goes here. It's just going to be y times rho of xy dA. Right? So that gives me my x bar and my y bar. And they actually call this the y moment and this the x moment, which I find very confusing. So I'm not even going to write that down. I'm just going to say that these are the moments, because I always get those mixed up and it's confusing. And so, because y is the y moment, the one where you integrate with respect to x. Well, there's a reason. It's because it ends up being a function of, well, never mind. I'm not going to go into it. But these are the moments, right? And so, I forgot. Oh, shoot. These are the moments, but they aren't the centers yet. Because remember, to get the center, we actually have to divide by the total mass. All right, those are the moments. To get the x bar, we're going to take this moment here and divide by, just like we did before, the total mass. So that's going to be this. And the y bar is going to be the moment for y divided by the total mass. That's the correct formula for x bar, y bar. Sorry, I forgot we have to divide by the total mass to get these, just like before. Okay. So what you do to do the problem, you find the total mass, you find the moments, and then you just divide. And that's how you get x bar, y bar. Okay. So what I'm going to do, I think I'm going to leave this problem for you to look at, and then we'll talk about the solution. I'd like you to try to work it out. Right? Try to do all these integrals and try to work this one out, and we'll talk about the answer on, well, tomorrow, Wednesday. Okay? So let me just show you the problem again if you want to copy that down. All right? We're finding the center of mass given this density in this region. Okay? So we'll discuss solution on Wednesday. But I basically gave you the whole procedure, right? You just find those things. The moments, the total mass, these are just things we've been doing all along. And then we can also do centers of mass in a volume. So I'd also like you to think about how would you extend this to find the center of mass of a meteor going through space, a three-dimensional volume. How do you get the very center of mass of that thing? What would the formulas be? Well, first of all, think about how the density is going to be defined. It's going to be a density at any point within that object. So it's going to be a function of x, y, and z. So you're going to be given a density that depends on x, y, and z. And then you're going to find the center of mass within that three-dimensional object. I bet you can figure out what the formulas are for the center of mass, given what we've done so far. All right, are there any questions? I'm going to come back to my video here, if I can. I don't know if there we go. All right, center of mass. Any questions? Or if you still have homework questions about the older material, we can ask that too. Looks like everybody's not seeing any questions. Some of you are all set. So all right. So if any of you have run out of late passes, let me know, and I can, if you're using them responsibly, which I think all of you are, just let me know and I can credit you some more late passes. So if you didn't get around to finishing that assignment on the triple integrals or something like that, or even an older assignment, or if there's an assignment way back when that you just didn't get around to finishing, please email me, let me know. I can look into it and we can probably open it up for you, okay? So let's make sure we keep up with all the homework. Another important announcement, I should have said this at the very beginning. We have an exam coming up, all right? We have an exam. I'll get to that question in just a sec. We have an exam coming up Thursday of next week, all right? And it's gonna cover, let me just look at that schedule. Remember the schedule is posted. Yeah, it's April 30th is the exam. So Thursday of next week. It's gonna cover everything through this section, center of mass, and the next section, 5.7. Not everything, everything since the last exam. So sections, all of chapter 5. I'm just realized, it's very simple. It's covering chapter 5. It looks like we've covered pretty much every section in chapter 5. Yeah, yep, we covered sections 5.1 through 5.7. That's gonna be the exam. And that'll be the Thursday of next week. And so we have time for review there. I've got on the schedule here that Tuesday and Wednesday of next week, we don't have new material. So no new material next week at all. It's just gonna be reviewing Tuesday and Wednesday. Of course, that's just 2 days, before the exam. So you're gonna wanna start studying much sooner than that, this weekend. And then you can ask questions about it. I'm gonna think about, I'll tell you what kind of problems I'm gonna ask you to show your work on. You know what kind of problems I'm gonna ask about because that's what the homework's been about. Anything in the homework is pretty much fair game. But I'll have you show your work on a few problems like I did on the last exam. And I'll give you an idea about what kind of problems I'll ask you to do that on. And in this next exam, the work is going to be worth more points than on the last exam. I want to make it a substantial amount of your points. Okay. So exam next Thursday, chapter 5. Okay, we have a question here. Is there any way to go back to previous homework? Yeah, that's what I was talking about. If you want to go back to a previous assignment that's way overdue, just send me an email. All right, just message me and I can open it up for you. But you need to email me and I need to do it manually. All right, any other questions? Yeah, I'll open up, I'll make copies of the old assignments and so that you'll have them for review. So I'll have those freely available to work on. They won't affect your grade, but they'll be there for you to review. Anything else? Okay, so it looks like that's it. So stay healthy, everybody, and I'll see you tomorrow.